Let's understand overfitting and underfitting. These are model generalization issues in machine learning. Consider three models. The first one is underfitting, the second one is a good fit, and the third one is overfitting. Each model tries to fit the data points. Let's explore what happens in each of these scenarios. Underfitting occurs when a model is too simple to capture the underlying patterns in the data. It fails to learn even the basic relationships between features. Underfitting has high bias and low variance. It also results in poor performance on the training data and equally poor performance on the test data. Consider the coordinate system. It has features on the x-axis and target on the y-axis. The scattered data points are shown in blue color. The true pattern is the green dashed line. The underfit model represented by the red line doesn't fit well with training data. Overfitting occurs when a model learns the training data too well, including noise and random fluctuations that don't represent the true underlying pattern. Overfitting has low bias and high variance. It performs perfectly on the training data but has poor performance on the test data. Warning: the model memorizes instead of learning to generalize. Consider the coordinate system. It has features on the x-axis and target on the y-axis. The scattered data points are shown in blue color. The true pattern is the green dashed line. The overfit model represented by the yellow line tries to fit every training data point and does not generalize well. Let's see how to detect model fit issues. First, let's consider underfitting signs. In underfitting, the training error will be high. The validation error will also be high, and the error difference will be small. Below is the code snippet. From sklern.metrics, import mean underfit train underfit is equal to mean underfit of underfit and one stripit. Underfit is equal to mean underfit of underfit and one stripit. If train underscore error is greater than a threshold, and the absolute of train underscore error minus underfit is less than a diff underfit threshold, print model is underfitting. Now let's consider overfitting signs. In overfitting, the training error will be very low. The validation error will be high, and the error difference will be large. Below is the code snippet. From sklern.metrics, import mean underfit train underscore is equal to mean underfit of underfit and one stripit. Underscore is equal to mean underfit of underscore and one stripit. If train underscore error is less than a low underscore threshold, and underscore error is greater than a underscore threshold, print model is overfitting. Learning curves show how model performance changes with training data size. They are essential tools for diagnosing overfitting and underfitting issues. By plotting training and validation errors against the training set size, we can identify convergence of errors, the gap between training and validation performance, and the potential for improvement with more data. Let's consider the underfitting graph. The x-axis represents training examples and the y-axis represents error. The training error and validation error are converging at a high error rate. Let's consider the overfitting graph. The x-axis represents training examples and the y-axis represents error. There is a huge gap between training error and validation error. Training error is low but validation error is high. Let's explore solutions for underfitting. The first solution is to increase model complexity. Add more features or use a more sophisticated model architecture to capture complex patterns in the data. Below is a code snippet. From sklern.preprocessing, import polynomial features. Add polynomial features. Poly is equal to polynomial features with degree equal to 2. X underscore poly is equal to poly.transform of x. Train with more complex features. Model.fit of x underscore and y. Try increasing the degree of polynomial features gradually to find the right balance. The second solution is feature engineering. Create new features or transform existing ones to help the model learn relevant patterns. Below is the code snippet. Import NumPy as NP. Create interaction features. X of feature under 2 is equal to X of feature 1 multiplied by X of feature 2. Add nonlinear transformations. X of log underscore feature is equal to np.log 1 p of X of feature. X of underscore feature is equal to m4 of X of feature. Domain knowledge can guide feature engineering decisions. The third solution is to reduce regularization. Decrease the strength of regularization to allow the model to learn more complex patterns. Below is a code snippet. From sklearn.linear from import ridge. Reduce regularization strength. Model is equal to ridge with alpha equal to 0.01. Lower alpha. Model.fit of X and Y. Monitor validation performance while reducing regularization. The fourth solution is to change model architecture. Switch to a more powerful model that can capture complex relationships in the data. Below is a code snippet. From sklearn.ensemble, import random forest regressor. Use a more sophisticated model. Model is equal to random forest regressor, with underestimators equal to 100 and maximum width equal to none. Allow deep trees. Consider the trade-off between model complexity and interpretability. Let's explore solutions for overfitting. The first solution is to add regularization. Apply L1, L2, or elastic net regularization to prevent the model from learning noise in the training data. Below is the code snippet. From sklearn.linear import lasso, ridge. L1 regularization. Lasso is equal to lasso with alpha equal to 0.1. L2 regularization. Ridge is equal to ridge with alpha equal to 0.1. Train with regularization. Model.fit of X and Y. Start with a small alpha and increase gradually. The second solution is cross-validation. Use k-fold cross-validation to get more reliable estimates of model performance. Below is the code snippet. From sklearn.model_selection import cross-validation. Perform 5-fold cross-validation. Scores is equal to cross-validation of model X, Y, with Z equal to 5, and scoring equal to 9. Higher k values give more robust estimates. The third solution is feature selection. Remove irrelevant features that might be causing the model to learn noise. Below is the code snippet. From sklearn.feature_selection import, select k-best. From sklearn.feature_selection, import f_regression. Select top k features. Selector is equal to select k-best with sklearn equal to f_regression, and k equal to 10. X_selected is equal to selector inference of X and Y. Use domain knowledge to guide feature selection. The fourth solution is early stopping. Stop training when validation performance starts to degrade. Below is the code snippet. From sklearn.neural_network, import ML_regressor. Model is equal to ML_regressor with max equal to 1000, early equal to true, validation fraction equal to 0.2, and equal to 10. Monitor validation loss during training. Here is the best practices checklist. On the left side, it shows preventing underfitting, and on the right side, it shows preventing overfitting. For preventing underfitting, ensure the model has sufficient capacity to learn patterns, engineer relevant features based on domain knowledge, reduce regularization if performance is poor, consider more sophisticated model architectures, and validate assumptions about data relationships. Remember to start simple and gradually increase complexity. For preventing overfitting, use appropriate regularization techniques, implement cross-validation in the training pipeline, remove irrelevant or noisy features, monitor training versus validation performance, and collect more training data if possible. Remember to keep it simple when possible. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.